Hey everyone, welcome back to Math Without Numbers, the weekly YouTube series where I show you cool math stuff and try to get you to buy my book. So this week I want to show you two cool little puzzles that both have to do with tiling. The puzzles are pretty similar to each other in the way that they're stated, but the solutions are very different from each other. So let's jump right in. This one you start with an 8x8 board like a chessboard or a checkerboard. But the special thing here is we're actually going to remove two opposite corners. So the question is it possible to tile this board using dominoes? And by a domino, I just mean two blocks next to each other. You can try this for yourself, but usually what happens when you start doing this, and I'll show you one example right here, you run into a problem where you usually end up with like a T shape left over, and you can try it over and over again, and you're always going to end up with that kind of problem. So the question isn't really, can you fill this in perfectly with dominoes? I'll tell you right now that you can't. The real puzzle is to figure out why this is true. Why is it impossible to cover this grid with dominoes even though there is still an even number of squares remaining? So I'll show you a proof right now. So this is the trick, and this is a really neat trick. I wonder how someone came up with this for the first time because it just seems too clever to come up with. The basic idea is to color this in as if it's a checkerboard. So I'm going to alternate coloring in every square either blue or white. Oops. So once you've colored it in, the thing to notice now is that every domino is going to cover one blue and one white square. No matter where you put the domino, you're always going to be covering one blue and one white square. And that's important because originally a full checkerboard has an equal number of blue and white squares, but when we removed these opposite corners, we removed two squares of the same color. So we have overall more blue squares than white squares. And that's going to be a problem. We're always going to be left with a situation where there are three blue squares and one white square left. That's why it's impossible to tile this board with dominoes. All right, time for the second puzzle. This one's about triominoes, and we're going to specifically be talking about the L-shaped triomino. Triomino just means a domino, but it has three squares. So this one's pretty similar. Again, we're going to start with an 8x8 grid. And I can tell you right now, you're not going to be able to tile this grid with triominoes because this isn't a multiple of 3. Instead, what we're going to do is we're going to remove one square from this grid, any square at all. And now the question is, this leftover grid, is this possible to tile with triominoes? And you can think about it if you want to, but once again, I'll tell you the answer right away. It is always possible. So the real puzzle is not whether it's possible or not, but why it's always possible to tile this grid with triominoes no matter which square you remove. A good trick if you're stuck on a problem in math or in general is to just try to answer a simpler version of the same problem. Instead of using an 8x8 grid, what if we just use a 2x2 grid? A 2x2 grid with one square removed, you're definitely going to be able to tile that with a triomino because it's literally just a triomino. So that works out just fine. Now what if you're dealing with a 4x4 grid? Since we already solved this in the 2x2 case, I'm going to break up the 4x4 case into 2x2 grids. And notice one of these, since it contains the missing piece, is already just a 2x2 grid with a piece missing. So we know that this is possible to tile. What do we do with the other three? This is the clever part. We're going to remove the inner facing square from each of these smaller grids. And now what you're left with is three more 2x2 squares that have a piece missing. So we know this is tileable, and this is tileable. And then at the end, we can throw in one last triomino that covers these three squares in the middle. And now maybe you see where this is going, but we're going to do the exact same thing with the 8x8. So again, since we've already solved the 4x4 problem, we're going to start by breaking this up into smaller 4x4 grids. One of these is going to be a 4x4 grid with something removed, and we already know that any 4x4 grid with something removed can be tiled with triominoes, so that one's done. And now for these other three, we're going to remove the inward facing corner ourselves. We're left with three more 4x4 grids with a single square removed, so we know this is tileable, and this is tileable. And then at the end, we can add one last triomino in at the middle. So there you have it, a proof that any 8x8 grid with one square removed is tileable by triominoes. That's all I got for you this week. If you like these kind of videos, be sure to hit the subscribe button, maybe get some post notifications too. Remember to buy my book. If you want to learn more about some of the stuff I talked about today, you can look up these terms. We're going to be coming back with new videos every Tuesday, at least until the book comes out, which is January 5th. And maybe a little bit past that if I have more I want to say. See you next week.